To analyze a chemical sample at the molecular level, you must first strip it of neutrality. Molecules are ionized, turned into charged particles, and accelerated out of a source chamber. The challenge then becomes manipulating their motion to separate them strictly by their mass-to-charge ratio. That physical separation happens inside the mass analyzer. It is the active environment where raw chemistry is converted into readable data. Decades of engineering have refined this process, resulting in two entirely dominant, yet physically opposite architectures. The first is time of flight. It isolates ions by measuring their velocity over time as they coast through a static, field-free vacuum. The second is the quadrupole. Instead of a static vacuum, it filters a continuous stream of ions in space using complex, dynamic, oscillating electric fields. Deciding whether to analyze a sample by dispersing it in time or filtering it in space dictates the absolute boundaries of what a modern laboratory can detect. A mass analyzer is a highly specialized physical obstacle course, one that must be tailored exactly to the thermodynamic state of the sample entering it. Time of flight is an inherently pulsed technique. Ions cannot enter in a continuous stream. They must be generated and accelerated in discrete packets. Equation 11 shows the mathematics of this initial acceleration phase. An extraction pulse applies a specific voltage, granting every ion in that packet the exact same kinetic energy, regardless of its mass. Because that kinetic energy is uniform across the packet, equation 12 reveals the direct physical consequence. An ion's velocity becomes inversely proportional to the square root of its mass. Lighter ions must travel faster. This schematic details the physical layout. After acceleration, the ions enter a field-free drift region, typically a tube 1 to 3 meters long, where no further forces act upon them. The mass spectrum is generated by recording the exact arrival time of the ions at the detector. Because of their higher velocity, the lighter masses arrive microseconds before the heavier ones. There's a critical engineering flaw in this linear design. The initial ionization process is imperfect. Ions of the exact same mass will inevitably enter the tube with a slight spread in their initial kinetic energy. That slight energy spread means identical masses will arrive at the detector at slightly different times. The result is broad, overlapping peaks that destroy the instrument's high-resolution capabilities. The physical solution to peak broadening is the reflectron, replacing the flat detector with an electrostatic mirror. This field acts as a highly tuned braking system. When identical masses with different kinetic energies enter the field, the faster ion penetrates deeply into the mirror before its path is reversed. Because the faster ion takes a physically longer path through the reflectron, the slower ion has time to catch up by taking a much shallower path. This perfectly aligns their exit trajectories, ensuring ions of the same mass hit the secondary detector at the exact same microsecond. Ultra-high resolution is restored. Because it relies on a field-free vacuum, TOF boasts a practically unlimited mass range, routinely analyzing fragments over 100,000 mass-to-charge units, all while capturing data in fractions of a millisecond. Time of flight is the ultimate temporal racetrack. Its ability to handle massive, intact ions without losing them in complex electrical fields makes it the analytical standard for large biological molecules. The quadrupole mass analyzer abandons the vacuum foot race entirely. Instead of observing passive flight, it forces ions through an active, continuous gauntlet. This diagram illustrates its architecture. The system consists of exactly 4 perfectly parallel, electrically connected cylindrical or hyperbolic metallic rods. A steady DC voltage and an oscillating radio frequency voltage are applied to opposing pairs of these rods. As an ion attempts to travel straight down the z-axis, these alternating voltages actively push and pull it, forcing the particle to oscillate wildly in the x and y planes. This creates a strict stability window. For any specific, locked ratio of RF amplitude to DC voltage, the complex equations of motion dictate that only one exact mass-to-charge ratio will survive the journey. The correct mass maintains a stable, bounded oscillation, successfully threading the needle through the entire length of the rods to reach the detector. Figure 8.2 maps the alternative. If a mass is even slightly too heavy or too light, the electrodynamics force it into an exponentially increasing wobble. These incorrect masses eventually strike the physical metal of the rods. They are instantly neutralized and permanently scrubbed from the analysis. To generate a full spectrum, the instrument does not wait for ions to arrive over time. It rapidly sweeps both the DC and RF voltages, sequentially bringing different masses into spatial resonance, one after the other. Quadrupoles are compact and highly rugged. While TOF requires accelerating potentials of several thousand volts, a quadrupole operates on just 5 to 30 volts. Crucially, this design allows quadrupoles to tolerate relatively high background pressures without failing. In a TOF analyzer, high pressure causes ions to collide with background gas in the drift tube, ruining the strict timing required for data collection. Because the quadrupole relies on spatial filtration rather than perfect timing, its pressure tolerance makes it the perfect analyzer to bolt directly onto the back of a continuous flow gas chromatographer. The quadrupole sacrifices extreme mass range for rugged, continuous spatial filtration, acting as an uncompromising electrodynamic bouncer for volatile chemistry. Time of flight measures the passive decay of velocity. Quadrupoles enforce active spatial resonance. The choice is never arbitrary. It is strictly dictated by the physical state of the sample. If an analyst is vaporizing massive, fragile proteins using rapid, discrete laser pulses, the instrument must be a TOF to handle the extreme mass and capture the pulse data. If an analyst is separating a continuous, high-pressure stream of small environmental toxins from a chromatograph, the instrument must be a quadrupole to keep up with the continuous flow. One requires setting up a perfect starting line and timing the race. The other requires building a dynamic obstacle course that only one specific runner can survive. The final spectrum, whether it shows a few massive intact keaks or thousands of tiny fragments, is entirely dependent on the physical constraints engineered into the analyzer. Chemical analysis is an exercise in applied physics. Mastering these principles lets scientists engineer physical rules that force the molecular universe to reveal its identity.